Thank you. So I'm glad I finally made it here. Tried to come last night, but they canceled all the planes from San Francisco, including mine, so I came in this morning. Haven't gotten a chance to talk to all of you as much as I would have liked. But I'm here today to, as he explained, I am the chair of the Physics and Astronomy Department at Sonoma State. It's about an hour north of San Francisco. We're in the wine country, very lovely area if you ever want to stop by. I also run a group of people that do education and public outreach, and have been doing this for about 20 years now. And so originally all my money was from NASA, the Fermi Gamma Ray Space Telescope, the Swift Gamma Ray Burst Explorer, XMM Newton, NuSTAR. But about 10 years ago, I was asked to give advice to LIGO on their program advisory committee. And so I gave them advice about education and outreach for about 3 years. And then as soon as I got off the committee, I joined the collaboration. So I've been really happy to find another way to study black holes and neutron stars, which is what I did for all of my career, but looking at X-rays and gamma rays. So I'm here to tell you and give you stuff that you can use with your students in your classroom. So how many people here are high school teachers? Pretty much everybody. Okay, that's what I wanted to know. All right, good. So this is what I'm going to talk about. I'm going to go through the guide. Now, I actually printed out copies of the guide. We put them on all the chairs that had people's stuff on them, but we didn't know where the rest of you were sitting. So if you did not get a copy of the guide, there's more on the table over there. I would encourage you to get one. And then I'm going to tell you about some online courses for LIGO that we have been developing for the past couple years. We've been teaching them. We got another one coming this summer. Hope those of you who teach AP Physics at least will consider signing up. And then I'm going to do a big reveal of our poster here. Then everyone's going to get to take home a poster as well, and we have some hands-on activities we're going to be playing with. So this is a scene, a little more than a year ago now. There I am at the press conference. This is Ben Owen, who works on Pulsars for LIGO and was one of my students a long time ago. So it was really cool that now I'm in a collaboration that he's been in for even longer. And I was asked by NSF, as the discovery news percolated through the collaboration, to do a very quick and inexpensive educator's guide to explain this to classroom teachers. So that is the thing that I printed out and brought you all copies of. If people didn't get copies and you want to raise your hand, we'll try to get someone to bring them to you. But here it is, hot off the presses. So this guide, because we had only about a month to do it and not very much money, we basically adapted material from other things that I had already done for NASA, including our big ideas in cosmology online curriculum, which I'll talk more about later, and classroom activities that had been developed for the Fermi Gamma Ray Space Telescope and other NASA missions. So in this guide, you will find the following sections if you want to look at them. We have background sections on gravitational waves, the signals from the universe, gravity from Newton to Einstein, the direct observation of the first gravitational wave signal by LIGO, and background about black holes. This guide includes new visualizations. For example, I have a wonderful artist, her name is Aurora Minette, and she did this spectrum of gravitational waves versus how strong they might be in strain, the H that you had heard about earlier today. Because just like electromagnetic waves, gravitational waves can occur at a whole bunch of different frequencies. The ones that LIGO has seen are up here in the hundreds to almost 1,000 hertz. Bigger systems with heavier masses will make slower waves or longer wavelength waves. Really big systems, even longer wavelength waves. And the longest wavelengths of all would be the imprint of the Big Bang on the cosmic microwave background that creates a polarization signal. We also have some material in there that addresses popular misconceptions. I'm sure you've all seen this kind of depiction of the curvature of space-time due to the presence of a mass, right? And the larger mass has more of a curvature of space-time than the smaller mass. We physicists call this an embedding diagram. The problem is that it makes it look like space-time is this flat sheet, and that rubber sheet analogy is used, pretty much anywhere where people talk about space-time. But that's not really what it is. What it really is much more like this. Right? That curvature, that warping is in all of the dimensions, including time, which we can't draw, even as cleverly as we try to draw it. Okay, so it's important to keep those kinds of things in mind, and that's all sort of explained in here. And then we have classroom activities. So later, you're going to get to do a cheap version of this one, and I was trying to do it with pulsars, but unfortunately I didn't get quite enough batteries, so some people will have to just do 2 black holes like this one, and other people can maybe do a black hole and a pulsar. But the idea here is, and this is without the weight, so if you make this with tennis balls and you put a weight and you make much longer string, I didn't really feel like bringing a whole bunch of weights, you can just take 2 of these and spin them around and watch them coalesce. And if they're shining lights out so that they look more like pulsars, then it is a cooler effect, but you'll get to try that for yourself later. So this model came from, well, at least the pulsar version of this model, came from an activity that we developed for the Fermi Gamma Ray Space Telescope, which is what these handouts are that are on your chairs, and the instructions for the pulsar version are on the back, in case you're wondering why I'm giving you something about Fermi at a LIGO meeting. But that's where the original pulsar activity came from. We'll be able to play with that, and at least 20 of you will get to make some pulsars later. And I'll talk more about the actual ingredients in the model. But that was our first adapted classroom activity. Our other adapted classroom activity uses my handy-dandy Spacetime here. This is an embroidery hoop with spandex fabric, and at the end of the educator's guide there's a shopping list for all the parts that I'm showing you today. So we like to make the Spacetime this way rather than this way, although technically it works just almost as well. But if you notice, this Spacetime has the rim of the embroidery hoop facing up, so that when, in the Fermi case, I put in a supermassive black hole in the middle of my Spacetime, and I launch some stars around it, they don't go shooting out all over the room because I've got the embroidery hoop facing up. Okay, if you can't see, just come on up and look. You don't have to stay in your seats. So in the case of the LIGO model, we replace our 4 million solar mass black hole, like the one that's at the center of our galaxy, with 2 LIGO-sized black holes. These are each 30 solar masses, pretend. And this is the really cool part now. I hope you'll be able to hear this, but I'm just going to make them orbit around each other, and when they coalesce, they're actually going to make a chirp sound. Can you hear it? I'll do it again. You hear the chirp? You hear the increase in frequency at the end? So it's pretty cool. So anyway, these are my LIGO black holes. You'll get to play with these later, after the talk. And oh, by the way, feel free to interrupt me with questions at any point about any of these things. So another fun thing we did was the astronomy picture of the day. February 11th is the day we held the first press conference announcing the discovery of the first gravitational wave event. And my wonderful artist, Aurora, redrew the signals from the 2 observatories overplotted and interpreted the actual supercomputer calculations of the real, official solving of the general relativistic equations that produced things that look sort of like this, and then she drew versions of them. And it was really a lot of fun because I've been on the board for the astronomy picture of the day for a while, and so I worked with them if anyone was paying attention on that day, they put up a blank screen, a black screen. And so this is a placeholder, and the real APOD will be released following the LIGO press conference. And then when the press conference started, they pulled the black screen, and everybody got to see this really cool image, which in our mind has become rather iconic. Okay, so moving on. So one of the things that my group has done is we've developed this entirely online curriculum. It's being sold by Great River Technologies, Great River Learning. And it's for general education college students, so it uses only algebra, so you could use it with high school students, no problem, if you were so inclined. We wanted to do a totally online curriculum because A, most of the colleges are trying to figure out a way to do online teaching to try to save money. Of course, it cost me $1 million to develop this curriculum, masses money, so it wasn't a way to save money to start with. Maybe now it is, now that it's developed. But it's easy to update, and in fact, as soon as LIGO announced the discoveries, we updated the part of the curriculum that included the discussion of gravitational radiation so we can keep it current as things evolve. But some important features of this curriculum is that we did extensive education research before we developed this into what it was that students did and did not understand about the origin, structure, and evolution of the universe. And gravity is one of those subjects. We use real data in a lot of our interactive activities, and we've extensively tested this purely online, flipped classroom, you name it, we've tried it all sorts of different ways. So these are the 18 chapters. Now I did 2 different online courses so far for AP high school teachers or community college teachers of lower division physics. And in the first course that I taught, we had people buy these 4 chapters, and then we developed some new materials. So I'll just concentrate on showing you stuff from chapter 10. So in chapter 10, which is all about general relativity, we talk about how, Newton's concept of the force of gravity is really just a consequence of the curvature of space-time due to the presence of mass and energy. And then we look into and do problems about curved space-time, including time dilation, gravitational redshifts, gravitational lensing. And we managed to come up with a simple way of describing curvature. How do you tell if something's really curved? And apply it to 2- and 3-dimensional models. But since we have good internet here, rather than stick with my PowerPoint for the next little bit, let me actually just show you what it looks like online. And it's right here. So here's the beginning. Here's the beginning of chapter 10. And so here are all the different sections: the equivalence principle, gravity and curvature, then the test of general relativity, the source of gravity, wrapping it up. So what happens is that let me just go to the first section. Every subsection, let's see what you can see here. Well, every chapter starts with a video. Actually, I think I'm going to try to show the video from the PowerPoint, just in case there's a time delay with the connection to there, because I tested this and this works.
Close your eyes and imagine yourself in a comfortable room. Like a small recording studio, the room has no windows and is soundproof, so there is no way to see or hear the outside. There is an exit, however, and just before you are about to leave, a voice over a loudspeaker says, "Be careful, watch your step. You are about to exit a moving vehicle." How could you tell if you were in a moving vehicle as opposed to in a building? You might wait to see if you feel yourself slow down, or if you feel the vehicle hitting potholes or going around curves in the road. But if you are moving at a constant speed over a smooth, straight road, what could you do to determine if you were moving? What if, instead of saying that you were in a moving vehicle, the voice over the loudspeaker said you were in a rocket in space, accelerating at 1g? The acceleration, due to the Earth's gravity, is 1g as well. Are you really in space? How could you tell if the voice over the loudspeaker was telling the truth or not without leaving the room? Albert Einstein had similar thoughts that led him to develop the general theory of relativity. But this theory doesn't just apply to hypothetical situations of windowless rooms on accelerating rockets. It is our most accurate theory of gravity and is important in our everyday existence. If the general theory of relativity had not been developed, our present-day world would be very different. For example, GPS systems rely on the results of general relativity. If GPS satellites use Newtonian gravity as the basis of their calculations, the positions produced by the satellites would be incorrect, and they could not provide accurate directions. General relativity also provides a vital perspective for our understanding of objects, like black holes, and even the evolution of the universe. Without it, our understanding of nature would be far less complete.
So that's just an example. We have a video that starts out every chapter to try to elicit what the students are thinking, sort of set the stage for what's coming after. And then the next thing we do for each subsection, we have a dialogue between students where the students, a lot of the words that are in these dialogues were actually taken from interviews that we did with real students as we were doing our education research to inform the design of the course. And so just like real students, they're not usually all right or all wrong. They get things a little bit right, a little bit wrong, a little bit mixed up. So we have these interesting discussions between students, and then the students who are taking the class are asked to say who they agree with and why, or if they don't agree with anybody, or what they really think is going on. So this is just an example. And then there are conceptual problems, there are numerical problems, and then there are interactives. And the end of every chapter, we have an interactive. This one is about a pulsar going around a star. And so you can start it up. Oops. At least I was able to start it up when I was doing this earlier. All right. Maybe it doesn't work in presentation mode. We'll try going to the actual website. Of course, all the things you test never work when you actually try to show them to people. That's a rule in experimental physics, in case you're wondering. So this is the same activity here. Let's see if it works now. Okay, so if I start it up, all right, that's good. So here we have our pulsar, and you can see it pulsing, and it's going around this star, and you can see the evenly spaced pulses around going across the bottom. And now you can turn on Doppler shift and see what happens. Anybody want to predict? It's coming towards you. The pulses are closer. It's going away from you. The pulses are further apart, right? Okay. Then you can turn off Doppler shift and turn on gravitational redshift. Okay, so now what do you think is going to happen? It's going to be in the gravitational well of that star when it's near that star, right? So what's going to happen to the spacing of the pulses as it comes around near that star? Right? Takes a little longer to climb out of the gravitational well, so the pulses are further apart, right? And then you can turn them both on at the same time. Right? So this has all been, the effects of this has all been sort of calculated or maybe slightly exaggerated in the calculation. And then there is a series of questions that the students are supposed to answer about the interactive. So this is typical of one of our wrapping it up activities at the end of the chapter after they've worked through all the other conceptual problems, all the other numerical problems. There's, in most chapters, many interactive things like this. A lot of them actually use real data. So what's really cool about this curriculum is you don't have to buy the whole curriculum. You can just buy whatever chapters you want to have for your class. So it makes it very flexible. Okay, so the reason that I'm really talking about that is because we used that unit and 3 other units in the first online class that I did on behalf of LIGO. So in 2015, so that was before LIGO made the discoveries, we did a course called LIGO Waves and Gravity, and It's, as I said before, it's aimed at people who teach first-year calculus-based physics. Okay, so that would be AP high school physics or first-year college physics. And so we surveyed the teachers to find out how they taught electricity and magnetism and special relativity. We assumed that nobody knew any general relativity, which was a darn good assumption. And then at the end of the online class, the teachers had to write reflections about how they thought they could use the materials that they just learned with their students. And so this first class had 7 units of material. The ones that are from big ideas, so about light, about classical physics, special and general relativity, I can't put online for free because they're being sold by this publisher that I'm partnered with. But the new units that we developed ourselves as part of this NSF grant to do LIGO education are available online. They are free. You can still see them. I can show them to you if I keep playing with my browser here. I guess I have to go to a new place. So if you don't remember any of the websites, this is the only one you need to remember for almost everything that I'm showing you. So epo.sonoma.edu is my group website, and then /LIGO takes you to all the stuff we've done that's freely available for you to use about LIGO. And that first link is to the educator guide, which you all have a copy of now. The second link is from the 2015 course, which I will now click on and show you. So this is all the free material. And so for each one of these units, we have a PDF file that has text with homework problems in them. And then sometimes we have additional handouts that are mathematical background things that could help you, or other computer background things that might help you. So learning more about light explains why electromagnetic waves come from accelerated charged particles and the dipole nature of light, in contrast to this is the most mathematical thing that we've done, and it's really pretty mathematical because it's hard to get away from it if you're going to do GR, but we tried our best to make it as simple as we possibly could. This handout called Geometry and Gravity for Weak Fields and the associated math supplement, by the time you get to the end of it, you will get the answer to the question that somebody asked earlier, which is, how do we know that the gravitational waves travel at the speed of light? And you will also get the answer to, how do we know that gravitational waves come from time-varying quadrupoles, right? Not dipoles like electromagnetic radiation. Okay, but it is very mathematical. We are going to revisit that in this next summer's course, because I think people need to see that. This unit, Astrophysical Sources of Gravitational Waves, is going to be updated because this was done in 2015 before the discoveries were made. So I'm going to update that one for this summer's course. And then there's just all sorts of other resources, papers, interactives, websites, and things like that about all these other topics. So special relativity, general relativity, gravitational waves, and black holes. So that was what was in the 2015 course. Here's some comments from the teachers that took the course. I was particularly proud about this one because I still think it's sort of hard to understand the general relativistic geometry and gravitation in weak fields, but we tried our best to motivate what we were doing physically. So then we made the big discovery. So that changed my view of what I should do for the next year's course. So the course in the summer of 2016 was all about the detections, and it had a similar structure. I'll show. And we developed all the material for that one ourselves, and so that's linked right here. And so this is really, really a good resource, and it isn't anywhere near as mathematically complicated as the little bit of GR we snuck into the first year's course. So we have videos, and who's seen this video before? Have you ever seen this video? Well, I know the LIGO people have. This is just a really cool video that came from PhD Comics, which if it works, I'll show it.
What is a gravitational wave? It's a ripple in the fabric of space and time. Imagine that space is a giant sheet of rubber. Things that have mass cause that rubber sheet to bend, like a bowling ball on a trampoline. The more mass, the more that space gets bent and distorted by gravity. For example, the reason the Earth goes around the sun is that the sun is very massive, causing a big distortion of the space around it. If you just try to move in a straight line around such a big distortion, you will find yourself actually moving in a circle. That's how orbits work. There's not an actual force pulling the planets around, just a bending of the space. Gravitational waves are produced whenever masses accelerate, changing the distortion of space. Everything with mass and/or energy can make gravitational waves. If you and I started to dance around each other, we would also cause ripples in the fabric of space and time, but these would be extremely small, practically undetectable. Now, gravity is very weak in the scale of other forces in the universe, so you need something really, really massive moving very, very fast to make the big ripples that we can detect. How would you observe a ripple in space? If the space between you and me stretched or compressed, we wouldn't notice it if we had made marks on our metaphorical rubber sheet, for example, using equally spaced rocks, because these marks would also get stretched further apart. But there is one ruler that doesn't get stretched, one made using the speed of light. If the space between 2 points gets stretched, then light will take longer to go from one point to the other. And if the space gets squeezed, light takes less time to cross the 2 points. This is where the LIGO experiment comes in. It has 4-kilometer-long tunnels and uses lasers to measure the changes in the distance between the ends of the tunnels. When a gravitational wave comes through, it stretches space in one direction and squeezes space in the other direction. By measuring the interference of the lasers as they bounce between the different points, physicists can measure very precisely whether the space in between has stretched or compressed. And the precision needed is incredible. To detect a gravitational wave, you need to be able to tell when something changes in length by a few parts in 10 to the 23. It's like being able to tell that a stick 1 sextillion meters has shrunk by 5 millimeters. The effect of a gravitational wave is so minuscule and easily confused with random noise, you need a smart data analysis technique. Scientists hope to identify the patterns of gravitational waves by comparing the wiggles they measure in the experiment to the wiggles they expect from the gravitational waves. That's like trying to identify a song being hummed at a noisy party. A very, very noisy party. Imagine your whole life you had been deaf until one day your hearing was restored. You'd be able to explore the universe in this whole new way. That's why detecting gravitational waves is so significant. It's a completely new way of studying the universe. Anytime there's a new way to investigate the universe, we discover things we didn't expect. It's really about looking for new things we didn't know existed, examining the extreme edges of our knowledge of physics, and testing our theories about how the universe works.
Okay, so that's a cute video, except they should have had at least one woman exploring the gravitational waves. Okay, so for this class, we have little sections that you can download and read, and we've separated out the homework. And so we have homework about the actual observations, and then each section has tons of resources that are related to that particular part.
Could you show one homework problem just out of curiosity?
Oh, okay. Here's the homework. So there's a homework problem. If you can see most of it anyway. I don't think it's all going to fit. There it is. So there's a homework problem. Some of them are just things that you can plug in, like this one. Other ones are computational. And then other ones are even more different.
I think your narrator speaks too quickly.
Okay. I'll All right. Thank you. So then, for example, we also have some homework that involves using Excel spreadsheets and computational things. We have links to the LIGO press conferences. We have links to the LIGO websites for the detection of the events. Then this section, section 3, talks all about the hardware. So how LIGO works. You're already here to talk about that, I assume, although I didn't get here early enough to hear all of Lisa's talk, but I assume that's what she talked about. And for this section, we were able to got a little extra money from the National Science Foundation to develop this new realistic LIGO video. So rather than just the cartoon video that you'll see in the course, this was done with Kai Statz, who also made wonderful movies with people in them about LIGO. But we got the actual CAD drawings in an attempt to show people really how complicated this was. That's really, what it looks like if you were able to go there and go inside those buildings. And of course, the buildings weren't there, so you could see the whole thing. So then, for example, these are the seismic isolation chambers. And so the beam is going to start out, and this is actually the beam path drawn on top of the CAD drawings. This thing that's called MC is the input mode cleaner, which cleans up the signal in the laser beam to try to make it be really precisely 1064 nanometers. And these things called PR, or the power recycling set of mirrors and subsystem, which keeps the laser beam going around to build up the power. This is the beam splitter. Now we're going to go down the two arms here. We'll pull back out and look at what it looks like as we go down the arm. So the laser beam is going to go back and forth inside this vacuum cavity, building up in power. It's sometimes called the Fabry-Perot style interferometer because the beam goes in and mostly stays in, and only a little bit comes back out and back to the beam splitter. Now we'll fly down the arm of the interferometer into the final seismic mount. This is the quad pendulum suspension that I'm sure Lisa told you about. This is the test mass mirror that weighs 40 kilograms. Here's the little skinny glass fibers that are holding this thing. Then the laser beams come back together. Oh, here they come. Okay, they rejoin at the beam splitter. They go into the output isolation chambers. There's a signal recycling system. Helps build the signal strength up. Then there's the output mode cleaner, cleans the signal up. Finally goes to the output photodetector. As I'm sure Lisa mentioned, the normal state when there's no wave is for the two beams to cancel each other. And then when the wave comes through, that cancellation isn't perfect anymore, and so you start to see a signal come out, of course, extremely grossly exaggerated, stretching and compressing of the arms, but as the interference fringes change, you eventually get to see the final wave. And right now we're working on a voiceover narration for that so that you don't have to have somebody like me sitting and talking about it. Okay, so I wanted to show you just a little bit more of that course. So this whole section has many other interactive things that you can do. And the next section is all about the sources of noise. Now, beating down the noise is the main goal of people that work on the LIGO hardware, right? Because it's this little tiny signal and this huge amount of noise. And so we have a bunch of different homework problems about the different kinds of noise. So people can do simple calculations to sort of see how much noise should there be just from the shot noise and the photons? How much noise should there be from the violin modes of those little skinny glass fibers that big 40 kilogram test mass mirror is hanging on? And what should the frequency of that resonance be from those violin modes and things like that? And then we also have made a video, and I'm going to show this just because somebody was asking me about this before. About how the compound pendulum works. That's at the, for example, at the end, holding up the end test mass. There's 4 different levels. This is just a simple demonstration of 2 levels where you can see that if you're below the frequency, not a whole lot happens to the thing that's at the bottom, right? So this would be like the end test mass there. But as you start to wiggle it closer to the resonant frequency, then you can start to move the thing more. So anyway, just a little video just because somebody was asking me about that. We made one to put in the course to try to demonstrate this point. Right, so, and of course LIGO uses 4 stages of pendulum suspensions for that final test mass mirror. So, Anyway, just wanted to show you that because someone had asked a question about it before. And then the last real unit is all about how we pull the signal out of the noise in the data. And so it's a little tutorial on matched filtering, which is the technique that LIGO uses. And so we have people go through just basic things like fitting lines and looking at data that you might have fit a line to, and then some noisy data, and what happens when you have a template of a signal and that's from your theory and your actual data, and you slide the two past each other, and then when they line up, you get the best result, right? So it's an Excel spreadsheet exercise that walks people through that process. And then finally, Unit 5 ends with the LIGO Open Science Center, which is a place where there actually is your ability to go and look at the real data. So for the LIGO Open Science Center, we made our own version of the tutorials because I wanted people to be able to look at the results for all 3 of the events, the 2 confirmed event and the 1 that wasn't quite confirmed. And so if you have a Microsoft account, you can go over to this library. It's just linked from the course right here. And then you can run these tutorials and look at them. And so in the interest of time, I'm going to save that to after I get through everything else I want to show you. But then we can come back to it and I can show you how the tutorials work for those of you who would actually like to look at it. Okay, so that was the second year's course. So, but the LIGO Open Science Center is a great resource. It's not as user-friendly as I would like. I'm hoping that I'll be able to help them with that a little bit more. All of the tutorials are currently written in IPython. Does anybody know Python here? Who uses Python in their classes? Not a lot of people. Has anybody ever used the Wolfram language or Wolfram Alpha, Wolfram Programming Lab? I'm also thinking about maybe trying to recast it in terms of the Wolfram language, but I haven't thought it through that carefully. Examples of projects that people have done can also be found. Using the LIGO data can also be found at that website. And here's just some comments on the second year class. I think everybody really liked it. I was very happy to be able to do this. I know that a lot of teachers and a lot of community college instructors can get extra salary raises by taking continuing education. And so, in general, most continuing education courses are in pedagogy and not in physics. And so I had heard from a lot of community college teachers that they really wanted the opportunity to be able to take a physics class and learn some more physics, to help them, not just more pedagogy. And so, so we offer the class in that way. And this summer, my new class is going to be about testing general relativity using LIGO's gravitational waves. It'll start at the end of June. It's about 8 weeks long. It's about, my opinion, is 4 weeks worth of work, maybe not even that much. You can have 2 units of academic credit or 2 units of physics credit or 2 units of graduate education credit. We'll probably reuse some of the general relativity stuff that we've done before, but we'll have at least 2 new units on the classical test of general relativity and on how one uses LIGO data to test general relativity. And you can register right now if you want to take it. It costs, I think the cheaper version is the continuing education units. You can have 2 continuing education units for like $85. So it's not expensive. So I encourage you, I send a notice out on the 2-year college list for APT, but if there's some great high school teachers list, I wouldn't mind sending it out through that list as well. Okay, so another thing I've been working on is the Contemporary Physics Education Project. So they're the nonprofit group that started at Lawrence Berkeley National Lab that Sherry's part of. As well, and they're famous for those really big posters of particle physics things that you may have seen in the hall. Well, I decided that they needed to have something on gravitation, and so I joined. I started a new subsection on gravitation. We've linked all of these LIGO materials to their website, and we have made this poster. And you all get to take one home for free. So we are selling these through Amazon, so invite all your friends who didn't come here to buy them on Amazon. But because you came here, you will all get to take one of these lovely posters home. And as you can see, the centerpiece of the poster, well, maybe you can see it better that way. The centerpiece of the poster, and so that's why I was hiding them here, but we have rubber bands, is the APOD image that we created that I showed you before. But it also has text explaining Newton's view of gravity, Newton's view of black holes, Einstein's view of gravity, the indirect detection of gravitational waves from the binary pulsar system, and then an explanation of LIGO's discovery. And so everybody will get one of these to take home. Okay, so I'm still doing pretty good on time here. So in summary, for the talking part of this, we've created a whole variety of materials that might be useful to your classes. If you're interested in adopting any part of the Big Ideas course for your class or to get free access, just send me some email. Everything that NSF paid for is available for free through my website. The new poster can be ordered through CPEP directly. And now we're going to transition to do some things by hand. Okay, so we have these models, so now you all get to get up out of your seats. Put your computers down, get up out of your seats. We're going to go to the back. Although once people do that, they can come up here and play with the Spacetime as well. So I'm not sure what this will do to the video now that I'm walking to the back of the room, but oh well. Okay. Now, had I really managed to bring the right number of batteries, so nobody can have more than one battery, and unfortunately there aren't even enough batteries for everybody to have one. But the original Fermi activity involves a battery and 2 LEDs. Who wants to be the guinea pig? Would you like to be the guinea pig? Okay. So we hand this to the students like this, and we say, okay, light the lights up. But since you're a physics teacher, you will actually, be able to figure this out. Now what most of your students will do is they'll do this.
Yeah.
Right? Right. But you guys are all physics teachers, so you'll be able to figure this out, right? Most of the students try to plug the LED into the watch battery, right? Doesn't work, obviously. Then they'll start, and then they're like, it doesn't work. And then I'm like, well, okay, just keep playing with it. And, they're just playing around, and, maybe they'll get it right, and they'll get one of them lit up. Okay? And then I'm like, okay, now light up the second one. And then maybe they'll do this one the other way. And they're like, this one's broken, it doesn't work. And so then I get to teach them about LEDs, right? That you have to, look at the little legs. They're different lengths, So what did you do different between the one that's working and the one that didn't work? And then maybe they'll figure it out, right? So then once they have successfully done that, you give them a piece of tape. Tape the whole thing together, give them a string, stick the string in there, and then finally take the body of the star, here, grab yourself a piece of tape, mush the star around there, and you have yourself a pulsar, or at least it looks like one when you spin it around. So this is the original Fermi activity.
That's awesome.
Okay, and I really apologize for the fact that I don't have enough batteries for everybody. Some of you will just have to make black holes. They don't have light.
Modeling magic.
So this stuff is called model magic. Yeah. It's less stinky than Play-Doh and less slimy than clay, and it does dry out in a few days. But any teachers that are interested, I can give you the parts list of where we order all this stuff from. Because we do these in science fairs. We do them in the exhibit hall at the American Astronomical Society when the kids come in for EPO Day. We've used these with kids from the age of 4 all the way up to, grown-ups. It's just a lot of fun. It's a quick, easy thing. And if you buy the parts in bulk, it's really less than like $1 a person. It's maybe only 50 cents a person, something like that. So anyway, for LIGO purposes, you need to have 2 of them. Right, so that you can model the inspiral.
That's great.
Okay, so I invite all of you to come in, and even if you can't build a pulsar, so don't take more than one battery, since I have so few. But so make a black hole in a pulsar system and play with them, or just make two black holes and play with them. So I'll leave these behind for everybody. So take those in the front and play with the Spacetime group, which is also a fun thing for science fairs and open houses and things.
I'll leave the battery.
Thank you. We like it. Yeah, it's exciting. Involved. It really doesn't turn out to be that much. So, and basically the batteries will discharge within a couple days, which is about as long as it takes the model magic to harden as well. So people can do that.
Very nice.
Yeah.
Very interactive.
Yeah, it's a fun thing, except for all the missing batteries. I have tons of LEDs, but no batteries. I don't know. My admin's in big trouble. They're not sending me the right amount of stuff.
Your microphone went off. Did you turn it off?
No, I was turning that way. I was whispering something. I don't want everybody to hear.
I have a question about the string system. How does the period change as a function of time? Does it diverge in the same way as the?
I don't think we've ever measured it.
Really?
Yeah.
It should be a simple thing to
It should be.
do, right?
Yeah. It looks to me like it's going faster as the string gets shorter.
Yeah,
so,
sure is.
Yeah. So I think it's good.
Okay.
I think it's a good model.
Is that described in here? The string model?
The one in here, you don't have to where you make it really long and you have like a washer, and you just have the two of them together and you just drop the washer and
the balls.
Right, it wraps the thing up and makes them.
I see. The weight isn't knotted there.
No,
it's just,
no.
I see.
Yeah, you
Okay.
just start with the weight at the top and you
I
let
see.
go and it'll go down and spin them together.
So the difference between that and this is that these wrap. And this doesn't wrap.
No, it still wraps because you still started out by throwing the tennis balls around like that. Right. So you still sort of give the tennis balls. It just itself.
Oh, I see.
Right, and you can make a classroom-sized demo and hang it from a door frame.
So it's not. So this may be in fact a different law than without the weight, right?
It may be.
Yeah.
You're a theorist. I'm not a theorist. I just make up stuff for classrooms.
Activity?
Well, it's published right there.
No, I mean in a like American Journal of Physics or a physics teacher.
We never get around to doing that kind of thing. We're too busy training teachers and making up stuff to do in classrooms.
But this would be great for the physics teacher.
I'm sure that it would be. Yeah, and I probably should, but mostly just.
And I'd never heard of model magic before. That will become a hardened object after a few days?
After a few days, it hardens up, dries out.
It's sold in an airtight package?
How
do they prevent it from hardening in the store? Okay.
Oh, I see.
You have to open it up.
Yeah,
Okay.
it's sold in packages like that. I'm covering it up because I'm having private conversations with people.
Oh, okay. I wondered what was going on. All right.
For
anybody who's in Santa Barbara, the Radio Shack is closing down, and they have like all their LEDs and batteries like 80% off. So
When is that?
one right on State Street.
Okay.
So, but they're only open like 2 more days.
I should have driven over there and tried to buy a bunch of batteries.
I have.
Are we going to do a Q&A?
Yeah. Okay. So, let's see how we're doing. Yes. So, we have 2 different size black holes here, and a star.
The speed, the velocity. A question, when you said the Wolfram language, did you mean Mathematica?
No, he has a language as well. It's called the Wolfram language. So Mathematica is the first product that he did, and now he has this thing called the Wolfram language, and he has a thing called the Wolfram Programming Lab. which is a browser-based thing that can run all of Wolfram Alpha and stuff like that. So, and if people would, like,
you do it with these two? Let me see you do it so I can.
You just go. Oops. Come on, you. There we go. They don't go around. It's good if you can have the students hold these too. So, there we go. And you can hear the chirp at the end, right? Or you can get the one really big black hole. Well, that's a little hard. You can make much bigger versions of this with PVC piping and more spandex, but then it's really hard to ship them on planes. So yeah, so we stick with this one as our traveling space-time hoop. Okay, so yeah. So if people want to come back up to the front and we can do questions and answers. Other people are having so much fun with their pulsars, we can wait a few minutes.
That would be pretty much the same modular if in a solar system. Yeah.
Telling Nick that I have a sheet of material. It doesn't have checkers on it, so it's not quite so nice. But we don't even do it with the rings. We take meter sticks and I put them on the edges of the material and clamp it to the tables and like cover half the room with it.
This is my traveling sized one.
So, did you ship those here, or did you carry them on the airplane?
No, I shipped those. But I could have checked them if I wanted, because I have a really good box now.
I just wanted to see you carry them on the airplane, because they're my hat.
This was my space-time in my black holes in this box. Okay, so if people are done playing with the pulsars, can you come back up and I'll show you the LEGO Open Science Center? No, I think it's more like $10 or $15. The PVC version can make really big, but then I can't ship that one.
Do you want to get people back to the
Yeah. So if people could come back up now, I still want to show you the LEGO Open Science Center stuff and have a little time for questions.
Hello? Can we sit down and take?
Okay. So there's a few more things I wanted to
go sit down.
Go wrangle all those people up here.
We'll take questions right now, and then you guys can play as much as you want.
Okay, it was my goal to get everybody excited and out of their seats after lunch so you wouldn't fall asleep. So I succeeded in that goal for sure. Let me just point out a few other things. At the end of this guide is a shopping list for the stuff that are in the demos. So if you want to know where to get the cool space-time fabric or the embroidery hoops or any of the things, there's links where you can order that, and also where you can order the black holes. Ugh. These are we used to use lead, but then we had to cover them up because of students. We had to like wrap the lead weights and things. So then we found these nice stainless steel kind of bowls, which are perfectly safe. So I just wanted to point that out. Since we still have time left, I want to show you the LEGO Open Science Center stuff. And it's on here somewhere. Okay, here it is. So there's a couple other Python notebooks in here that if you wanted to learn Python, you could use, but they just seem to come with all of these Microsoft Azure notebooks. This one starts with downloading the data. So this is just to get all the data in play, and basically the way these Jupyter notebooks work is you just go to where it says cells and you say run all. So it just takes it a little while to get all the data, and then it's done, and then we can go back to this notebook and run the event tutorial for, say, the first discovery event, 150914. And I'm going to do the same thing here. I'm going to say run all. While it still says busy up here, you wait because it's still doing stuff, and you'll see what it does when it's finally done saying that it's busy. But basically, just ignore all that stuff. Okay. What it does is it has these cells, and it shows you the Python code. And I have made 3 different versions of this so that I can pick which of the events I want to do, and I can show you the difference between the 3 events if, I guess I'm not going to run out of time. So when you say run all, then what it does is, this is just sort of a walkthrough with some comments, although in my opinion it could use a whole lot more comments, of what actually happens in the LIGO data analysis pipeline. Although this is a very simplistic version of it, it is not exploring all possibilities. So we read in the data. In this particular set of data, there aren't any gaps. We're going to look at the data from H1, which is Hanford, L1, which is Livingston. Okay, so there's some data. Okay, not cleaned up in any way, not processed, right? So here's the data near the big discovery event. Now we're going to plot the amplitude spectral density. So this is the kind of curve that resembles the curves that Lisa, I'm sure, showed you, which is, oops, you can't see I can't see the bottom. Well, that's better. At least you can see the scale here. So this shows the sensitivity curve as a function of frequency. So strain per root hertz is a function of frequency. And you see these big noise spikes for various instrumental reasons. If you actually go through and do my problem about the violin modes that I was talking about with the skinny little fibers holding the big heavy mirror, you discover that the fundamental frequency for that is about 500 hertz. And lo and behold, there's this huge noise spike at 500 hertz. So that's coming from that source of noise, right? The resonance of these little fibers hanging this big mirror and its subsequent harmonics. So that's an interesting thing to look at. And then there's a calculation of if this signal was from binary neutron stars, how loud of a signal would it be? How far away could we have seen it? Now, the answers are right there. But in the case of the LIGO discoveries, these were 2 black holes, not 2 neutron stars. And the amplitude of the signal is proportional to the total mass of the system. We call it the chirp mass. So obviously, if you've got 60 solar masses worth of black holes that are colliding, you're going to get a much stronger signal than if you only had 2 1.4 solar mass neutron stars. So that means you could see them further away, which is why if these were binary neutron stars, you could only see them out to 74 or so million parsecs, whereas we saw these 2 black holes at 1.3 billion light years divided by 3. So, way more than 75 parsecs. Okay, so then they're going to whiten the noise. Then we plot some spectrograms. Now here's a spectrogram. So this is one of the things that people always look at. And again, you can see these big noise spikes at a frequency of 500 hertz from the violin modes, for example. But it's pretty constant. These noise spikes are, the main noise contributors are pretty constant throughout the whole time of the data. So that's the Hanford detector. There's